Um, thanks everyone for coming. It's my pleasure to introduce Dan Roth. Dan is a professor in the computer science department at the University of Illinois' Urbana-Champaign. And in addition to computer science, he also holds appointments in the departments of statistics and linguistics and in the School of Library and Information Sciences. He's the director of the Department of Homeland Security Center on Multimodal Information Access and Synthesis. He's a fellow of the ACM and the AAAI, and he has a huge breadth of work in natural language processing. And I recently saw his group's advertisement on the Corpora list that they've released their suite of NLP tools, which includes everything from sentence tokenization and splitting to part-of-speech tagging and chunking, named entity recognition, co-reference, and semantic role labeling. So I'm always excited to hear what Dan has to say. So take it away.
Okay, thanks, Chris. Thanks for coming. So I must say that in the few discussions that I've had here so far, I realized that I could have given 2 other talks, and it fits the interest of people here. So, but anyhow, I want to talk about basically something that we've been doing for the last, 5-6 years, which I call constraint conditional models, and we use this to support a lot of the stuff, not all, but a lot of the stuff that my group has been doing the last few years, formulating NLP problems as integer linear programming. And I want to talk a little bit about the inference and learning issues that come up, or at least some of them. So first I want to thank several of my students and postdocs that are involved in the talks that I'm going to talk about today, and of course the funders. And I want to start by making a request here that I think you can read. What is it? What does it say? Turn off your cell phone. Excellent. You're quick. So, so the reason I do it is not only because you should turn off your cell phone, is mostly because this is one way I think about natural language understanding. So it's a lot about interpreting multiple components, solving a lot of component problems, and then trying to put them together in the context of me putting this on one slide, or me asking you a question that makes sense, so you know that they have to be related somehow. So natural language understanding really is about making global decisions where many or several local decisions play a role, but there are mutual dependencies between them. So it's essential to make coherent decisions in ways that taking the interdependencies into account. So in the puzzle that I ask you, each one of the components had multiple interpretations, but in the context of putting them on one slide and asking you a question that basically meant that there is some meaning here, you could disambiguate them and solve them. So today I want to talk about frameworks that actually do this in the context of NLP. The question is how to support real high-level natural language decisions, and I want to talk about the inference component of it and the question of how to learn models that eventually are being used to make these global decisions. So as I said, I'm going to talk about a framework that allows one to exploit these interdependencies among decision variables, both in inference and in learning. And I'll try to devote some time to both. In inference, the question is how to formulate something that allows one to incorporate expressive declarative knowledge in decision making. And in learning, the question is how can we learn tractable, simple models and amplify them using these interdependencies to actually support eventually these decisions. So I'm really interested in solving this problem in the context of more interesting NLP problems like this. So this is a short story taken from a comprehension test that is given to 2nd or 3rd graders. They can do it. And basically, given the story, they are also given some 4 or 5 questions. And in this case, I rephrase the questions to be statements because I'm interested more in the textual entailment aspect of it. So the question is, are these statements correct in the context of this story? And you can see that in order to address each one of these inference questions, or any other question you have about the story, you have to understand a lot of things. For example, there's Christopher Robin, Chris, Mr. Robin. Is this the same person? Who says yes? Votes. Voting season.
Sorry, this is all three being the same?
Yeah. Who says yes? Who says no? Think again. Who says yes now? So the answer is, you know.
The answer is no, although there's a problem in that Mr. Robin is, doesn't actually refer to anybody. It's actually Mr. Mills, his father's name.
You don't need to know the truth. This is truth here. So in the context of this story, the answer is no. And you know that the answer is no, even though you have to think a little bit about it. And the reason is that there is some fact there, you know, his father, that actually gives it away. But you really have to do reasoning. And this is one example. There are many other problems in this text. You know, there are many pronouns, his, he, him, and so on, and you have to know what do they refer to. There are many relations that are expressed here. Someone wrote a poem. Someone wrote a book. Someone has written 2 books. And in order to really address a lot of the questions here, you really have to resolve each one of those, or many of the others that I haven't even mentioned and pointed to, and figure out how to put them together. So over the last few years, or 20 years in NLP, we actually made a lot of progress on each one of the individual projects. And what we really don't know how to do is we don't know how to put things together. And this is kind of what I call the inference problem. So this is my goal here. I want to think about these global decisions where multiple local decisions play a role, and think about how to take into account these mutual dependencies in order to address the global inference question. So currently in NLP, we think about these kind of problems, but mostly we think about simpler instantiation, simple structural problems, parsing, information extraction, semantic or labeling, and so on. And as we move up, and by the way, some of these problems we can think about them as just a single problem. We don't need to think about them as multiple components, although I would argue it's a useful way to think about it in many cases. But definitely as we move up in the problem hierarchy, moving to do textual entailment, question answering, and others, not all components can be learned simultaneously. Some of them, sometimes we must think about sub-problems, partly because some of the sub-problems we learned yesterday, just like you learned yesterday how to interpret the component in my puzzles. It's not something that was given to you as part of the decision problem. You brought it from home. And this is going to be more and more of the situation. And in many cases, knowledge-related sub-problems could become, first of all, it will become more essential to incorporate, and it will appear only at evaluation time. So our goal is really to incorporate models information along with prior knowledge in making coherent decisions. So I want to make decisions that on one hand respect the local models, you know, the interpretation of the and the or that you had before, and at the same time respect domain and context sensitive knowledge and constraint. So that's the goal, and I'm going to do it, I'm going to talk about some work that we've been doing. So my first part is going to be basically an introduction to the framework, constraint conditional models, and then I'm going to try to address some issues in learning, specifically constraint-driven learning, and some issues in inference, mostly focusing on more recent stuff that we've done in these, and try to give you pointers to some earlier stuff. So really, to think about the framework, I try to think about it as having really 3 key ideas. So the first one, which I call the modeling idea, is something that really is similar to the ideas that are at the basis of probabilistic modeling. I want to be able to separate modeling and problem formulations from algorithms, right? So this is something that it's common. I want to think about how to model problems, not think about how I'm going to solve them eventually. The second idea, which I call here the inference, is actually very different than the way I think about what's happening in probabilistic modeling. So I want to be able to keep models simple and nevertheless make expressive decisions via constraints or other ways of representing knowledge. So this is really different than the current trend in probabilistic models, where models become more and more expressive and complex. And the third idea is, the learning idea, is that even though we want to make expressive decisions, we can actually support these by learning rather simple models. And the idea is that global inference can be used to amplify simple models and even sometimes allow training with very minimal supervisions, because if you have multiple variables that interact in different ways, you can propagate information from those that you're confident about to others via some knowledge about the way they interact. So these three ideas actually are what I want to accomplish, and let me start by giving very simple motivation to this. So a lot of the problems that we deal with NLP, we think about them as pipeline problems. So they are not single classification problems, and we change several models. So there are several pipelines that we consider. You know, one could be start with part of speech tagging, move to identifying phrases, then entities, and then relations between them. And you can invent some other pipelines, and all of us are familiar with this. So clearly, pipelining is really a crude approximation for what we want to achieve. It's completely clear that it leads to propagation of errors. It's because occasionally, or in many cases, decisions that we make downstream may be easier and could be used to correct earlier decisions that we've made. Nevertheless, there are many reasons to use pipelines. Putting everything in one basket and making a global decision doesn't make sense in most cases. There are good reasons to think about pipeline. Earlier decisions could be more robust, could be simpler, and could support, maybe are essential to support and invent even vocabulary for downstream decisions. So how can we deal with it? So one way to think about it is, why don't we just think about some consecutive stages in the pipeline? For example, looking at entities and relations and try to do this together. So thinking about it this way gives a problem of this sort. So think about the information extraction problem, where I want to identify entities like Dole, Elizabeth, North Carolina, and I want to identify relations between them. I'm showing here two of the relations that exist between these three entities. There could be more directed relations between three entities. So let's assume that I've learned some local models that give me an interpretation for what could Dole be, what could Elizabeth be, and so on, and what could the relations be. So for lack of space, I'm only showing three possible values for each one of these. So these are conditional probability tables for the values that Dole can take. It could be a person or a location or other, and the values that each one of the relation can take. It could be a spouse of, or born in, or no relation. And the simplest decision, given that I have these local models, would be to take the mode and say, okay, these are my decisions. So I'm highlighting it here with the blue thing. Of course, if you look carefully at these decisions, for example, look at these three boxes, you see that I have two people interacting in the relation born in. Doesn't make sense. I want to change something. And the easiest thing to change here is to change the relation, the entity tag person to a location. Similarly, I can look at these three boxes, and again, I see that I have two people interacting in a relation born in. Again, doesn't make sense. It violates constraints that we may have on this, and in this case, I want to change it by changing the value of the relation. So, of course, there are many questions that you can come up with on this, and before the questions, this actually helps, significantly helps the decision-making, the global decision-making here. One important note before we even come to question is that this is a non-sequential model, right? This is a real graph that you have to make decisions on, and not just a sequence. But the key questions are, you know, first of all, why don't you learn jointly? Why didn't you learn everything together? And there could be multiple reasons. One of them could be that maybe someone gave you the entity model yesterday, and it was learned in a different situation, and you just want to use it in learning other things and improving other decisions. And it could be that in some cases, the decisions, the constraints between these two models became apparent only at decision time and were not available in learning time. And there are also theoretical justification for why sometimes I want to learn this separately. And the second question is, of course, how to do it. I mean, what are principal ways to guide this global inference? And clearly what's going to happen behind it is that I'm going to have some kind of an objective function. The details are unimportant now, that incorporates learned models with the knowledge that combines them. And this is what I'm going to call constraint conditional model. So a little bit more formally, what I have is an objective function like that, that has on the left side a weight vector lambda of local models, and f of xi's are my local models. You can think about them as features, you can think about them as classifiers, you can think about them as log linear models of different sorts, or combination of this. So it could be kind of simple things, single variables models, and could be groups of variables like HMM or others. And on the right side, I have a model, a way to model my constraints. So these in general are going to be soft constraints component. And again, I'm going to have a vector of rho i's, which are my penalties for violating constraints, and a component here that I'm thinking about as a distance metric that allows me to model how far a proposed assignment to the y variables is from the feasible set, given a constraint, for the legal assignments. And the distance itself could be either minus infinity if you want to deal with hard constraints, and then I can actually move this component to be below this and say subject to, or it could be something that is problem specific that allows me to model how much did I violate a specific set of constraints. So with this objective function that really, as I'm going to point out later, is something that in a sense all of us are doing in one way or another when we do NLP, it brings up two computational problems. So one is how to solve it, the inference problem. It's an integer linear program. You can think about it as solving it using linear ILP solvers. You know, there are good commercial packages, and you'll get exact solution. You can also think about different ways of using approximate solution, from cutting plans, dual decompositions, any other search technique that you like. And I want to abstract away this part now. And you can think about, and the second computational question is how to train these models. Training here means learning the objective functions, basically learning the lambdas and the rhos. And there are many interesting questions here. Do I want to decouple the learning of everything, or do I want to decompose these models? And of course, questions of learning protocols. How can I exploit the structure that I have, the constraints themselves, as a way to minimize my supervision? And I want to address some of these issues. And I want to start by giving a few more examples. So really, I want to think about this formulation of CCMs as a general interface that will allow me to easily combine declarative domain knowledge with data-driven statistical models. And I'm going to illustrate this with three examples. Typically, I choose these examples so that at least one of these models will be clear to anyone in the audience. I think in this audience, you will understand all the examples, probably better than I do. But anyhow, I'm going to run through these. So here is one example. Let's think about sequence tagging. So sequence tagging, think about, HMM or CRF. And then I want to augment it. So HMM CRF itself is just a linear model. So this is the left side of my objective function here. But let's assume that I have some constraints. For example, I know that I cannot have both A states and B states in the output sequence. So what are the options to model this? I can say, well, I can't model it with an HMM, so I'm going to learn a more complex model. Or I can say, you know what, I'm going to keep learning my HMM and somehow, using this right component, enforce that my output sequence will not violate this constraint. Or I can push my output model to less violate this constraint. And this is one way to use this right side here. Example 2, think about sentence compression or summarization. So again, the standard way of dealing with it is to learn some kind of a language model. So I'm denoting this as this linear model here, where the ijk indicates that I'm going to learn some trigrams, and I'm going to put into my summary sentence only the heaviest or the heavy components in my language model. And this would give me some representation, some summary of the document that I want to do. Of course, while it's going to be some kind of a summary, it's not going to be English or whatever language I want it to be, because it's not going to look like standard text. So, but I can impose some constraints. For example, I could say, if you choose a modifier to the summary, include also the head. Or I could say, if a verb is chosen into the summary, make sure it includes also its core arguments. So these constraints deviate from these simple linear models. And again, my option is learn a more complex model or just keep this simple model and impose this constraint using this right side of the model. And again, people have tried these kind of ideas, and it helps a lot. My third model is going to be semantic labeling, where the model is going to be just a bank of classifiers learned independently, and I'm going to impose some global constraints. So I'm going to give a little bit more details on this. I assume all of you know semantic labeling, so here's an example of what I mean by semantic labeling for the people that don't know. I want to be able to parse this sentence. I left my pearls to my daughter in my will as A, I am the liver, my pearl is the things left. To my daughter, that's the benefactor. And in my will is some kind of a location adjunct. So what is an algorithmic approach? So you learn a bank of classifier, two types of classifiers really. One type of classifier that basically prune the set of all candidate arguments into those that are legitimate arguments and those that are illegitimate, and it's binary classifier basically, and a set type of classifiers that basically type the arguments for each candidate argument that is left here or that is recommended here. I'm going to type it, basically color it in a specific color, whether it's A0, A1, A2, and so on. Really what we do is we don't just type them, but rather we learn a probability distribution over possible types, but I don't know how to show this here. The key step here, once I have this bank of classifiers, I want to go to the inference step where I'm going to use this estimated probability distribution given by the classifiers, use some structural and linguistic constraints to infer the optimal output. And basically the picture you have is something like this. You have a collection of candidates that are colored here in different colors, and I have a conditional probability distribution on each one of them. One option for me is to just choose the best one, and then I have a selection. And this selection in this case actually is illegitimate because I have this phrase that overlaps with this phrase. So it violates a constraint that in this formulation I don't allow arguments to overlap. I have to change something, and in this case what I'm doing is I change something here, and I'm choosing the null argument for this part, so this isn't an argument. That's the type of inference. It's important to realize that in this specific problem I'm actually solving in principle multiple inference problem per sentence. I'm going to solve one inference problem per verb predicate in a sentence. The interesting thing here is what knowledge can I bring into this problem. So there are many constraints. For example, I could say no duplicate argument classes, only one A0 per predicate. And I can write it as a linear inequality. I'm not going to go over the details, but you can think a little bit about it. Or I can say things like, if I have some argument of this type, I must also have some argument of another type in the sentence. Or if I have an argument of this type, I must have somewhere to the left of it an argument of another type. Notice that these constraints are actually universally quantified rules. They're not propositionals like the features that you're used to see. And again, I can translate each one of these into a linear inequality. It's not that difficult to do. The key observation that is known for many, many years is that any Boolean rules actually can be encoded as a collection of linear inequalities. So it's a very, very expressive language. You can do essentially whatever you want here. And this allows us to encode many other possible constraints. For example, you can say you can impose relations between the number of arguments. If I have a verb of this type, it cannot take more than 4 arguments. Or if I have a verb of this type, it cannot take arguments of this type, and so on. Even the difficulty of writing this as linear inequalities, this is a shameless plug to one of the tools that we've developed that is called Learning-Based Java, where we allow developers to encode constraint in a high-level language, kind of like first-order language, and the LBJ will compile it into linear inequalities automatically in a rather efficient way. Question?
Yeah, so is there any Java in the constraint language?
Is
or
there?
You just call it from Java?
We call it from Java, and we translate it, we compile it into Java, actually. So you write your code in learning-based Java, and it compiles it to Java.
And the Java code is going to generate aerobic constraints or something?
Yes. Gorobi, or we interface either with Gorobi or ExpressMP. And we generate the instance of the ILP solver. Okay, so the end, what you get is you get basically this ILP program. You minimize this objective function. And in this specific case, as I said, basically the model here, or the models that we put on the left side of the objective function are all independent classifiers. So it's only f of x, really, subject to a bunch of constraints that I showed. And the outcome is a pretty good semantic labeling that is also very efficient. So even though ILP is in principle a hard problem, in many NLP instantiations, it's actually working very well. And I must say that although we are using also approximation in some of the problems, I've been very, very impressed with Gorobi. I mean, from the time I started to work on this in 2004, I think there's been an order of magnitude or more improvement in the quality of the solver. So it's really good. Okay, so just to summarize this part, there are many ways to justify what we are doing here, and I don't want to go into all these details, but one way to think about it is that you can think about CCM is really the right objective function if you want to start with a probability distribution, a model that you've learned, and push it so that it satisfies a set of given constraints. This is really the right objective function. This is one way to justify it. You can also justify just by thinking about it as Markov random field, where the decision problems of Markov random field is also an ILP, or can be written as an ILP. And you can think about multiple ways, of course, to do it. I mean, the standard way for people to learn Markov random fields is essentially to do joint learning. And the difference in constraint conditional model is that we want to design it, or we want to emphasize the ability to basically learn component models rather than jointly learn, although you can also jointly learn. But the philosophy is that we want to emphasize the ability to learn component model and then make decisions while incorporating background knowledge globally. So that's really the key emphasis. Of course, this has to come with caveat that there are many formulations and everything can be done with everything. The question is what's easy to do in each one of the formulations, and this is what we think is easy to do with CCMs. Okay, so just to summarize the context of what I'm talking about. So you can think about you're given a collection of variables, these y's here, and the variables could be simple and could be complex. They could be in themselves, structure a model of some sort. And my goal is to optimize some kind of a linear objective function relative to this. In addition to this, I also have over the same set of variables something that you can think about as a constraint network, encoding the knowledge that you have about what values can be taken together and so on. And I can also encode this as a linear model. Of course, there is a joint probability distribution that represents this mixed model. The issue is that I don't want to learn this. I want to be able to learn the simple model on the left, or several simple models, and nevertheless make decisions with this combined model, with this complex model. So that's basically the philosophy. If you want to compare it to other models that exist, for example, Markov logic networks, the key difference is that while Markov logic network also provides a way to represent this joint model, the philosophy there is that they want to represent and learn the whole joint one. Okay, so before I summarize this part, some pointers. So there's been a lot of work in the literature using these models, using ILP formulation in general, in a wide variety of NLP problems, from summarization, coreference, information extraction, event extraction, temporal reasoning, dependencies, and so on. There is some theoretical understanding on training paradigms that I will not get to today. And there's a lot of work on inference, mostly approximate inference, bringing back ideas, on Lagrangian realization and others. And I'll talk a little bit in the rest of today, something about some more recent learning ideas and some recent inference ideas. And you can go to my tutorial page and see a whole tutorial on this that gives a pretty exhaustive set of pointers to what has happened. Okay, so let me move to talking a little bit about learning. And so I'm talking about this right box here, how to train these models. And again, training is learning these objective functions, and you can think about multiple issues that come up when you want to learn it. So some of them have to do with decomposition. Do I want to decompose the model here from the constraints? Do I want to decompose the model here to multiple components and learn them separately? And as I said, there's been some work and some understanding of when do you want to do what. And not surprisingly, the composition is good. You can see a summary in a recent MLJ journal paper that kind of summarized some of the early work in this direction. And there's been a lot of recent work on this. And what I want to talk about is going to be one learning paradigm in this context, and I'm going to motivate it with this information extraction problem. So this is a citation, and the goal with this in this problem is to parse this citation at the level of who's the author, what's the title, who's the editor, what's the book title, and so on. What you see here is actually an output of a simple HMM trained on not too many examples, but you can see that so basically this is the left side of my objective function. You can see that the results are pretty bad. Really violates a lot of natural constraints. And the question is, so what do we do? How do we get around these difficulties of learning with HMM? So there are standard solutions to this. I mean, the standard solutions say, well, move to a higher order model. Make a model more complex, more expressive. Of course, this will mean that we need to see a lot more examples. The question is, what if we only have a few labeled examples? What can we do then? So the real question is, can we keep the learn model simple and still make these expressive decisions? So the option I want to entertain is, can I constrain the output so that it makes sense? Or can I at least push my model in the direction that produces output that makes sense? And example of constraints are things that we all know and can express in an easy way. But for example, each field must be a consecutive list of words and can appear at most once in a citation. Really easy pieces of knowledge that are non-propositional. Really, they could have quantifiers, and they do have quantifiers in this. So in this specific example, which was chosen right, in fact, just incorporating the 10 constraints that we're using in this problem actually fixes all the problems. Doesn't happen all the time, but it does happen in this case. And this happens without changing the model. So just by adding this component to the model. So really, this is the philosophy, right? I want to be able to learn a simple model and make decisions with a more complex model. And in this case, we accomplish this directly by incorporating the constraint as a way to bias the decisions made by the simple model. So more formally, I want to think about it here in the context of semi-supervised learning. So in the standard semi-supervised learning, I'm starting with a model that is seeded with a set of labeled examples, and then I'm using this model to annotate a lot of unlabeled data, and I can send these examples back to the model and keep on running it this way. We know that in traditional semi-supervised learning, this could cause some problems because you can actually drift away from the correct one. I'm going to avoid this problem by incorporating constraints, and there are two places I can incorporate constraints here. One is when I label the unlabeled data, I can fix this labeling so that when I send it back to the model, I send more robust data. And of course, I can also incorporate the constraints at decision time. The algorithm that you're going to get this way is what we call constraint-driven learning, or CODEL. You basically start by learning a model, and in this case, I'm writing it as if I'm learning both the weights of the model. This was lambda before, now it's W here, and the penalty coefficients, although I can also separate these and learn them separately, and this is discussed in the paper, specifically in this recent paper. And then, once I do this, I'm going to iterate over my unlabeled data set. At every point in time, I'm going to do inference, and I'm going to use my learned model along with the constraints. I label the data, I put it back into my training set, and I'm going to keep on training. And of course, I'm also going to incorporate it into my model slowly. So basically, I'm going to weigh the old model with the new model as I do it. And this is a very simple algorithm which produces excellent experimental results, basically showing that you can encode a lot of information using this constraint, basically to replace a lot of training data. Other people, other groups have used this model or variations of it and showed also results. So just to illustrate the type of results you can get, so basically, again, this is my poor model, my simple model, and this is the way to enforce the data. What you see here is the blue line represents the performance you can get when you learn without constraint using 300 examples, labeled examples. The red line represents what you can do when you learn with these many examples and incorporate the 10 constraints, a subset of which I've shown before. So you start, of course, lower, but around 20 examples or so, you already beat the trained model with 300 examples, and you can do even better than that. So that illustrates a little bit of the sort of the value that you can get from this. Now, what has happened in this domain over the last few years is that people have extended it in different ways, and I want to talk a little bit about it. So one way to think about this model is really thinking about it as an EM algorithm. So really, you can think about it as the hard EM, which is one of the more popular variants of EM. So while EM estimates the distribution over all Y variables in the E step, in hard EM, we basically predict the best output. You can also think about it as using a delta posterior and think about this as what hard EM is doing. And constraint-driven learning, CODEL, can be viewed as a constraint version of EM. Rather, we are basically doing hard EM where we are constraining the input to belong to this feasible set that we have. Now, this is CODEL, but it's possible to derive a constraint version also of EM. In order to do this, you actually have to relax the notion of constraint to expectation constraints. And really, this has been done. Of course, this modifies the E step to the EM step constrained via this expectation constraint. And this really is an algorithm that was developed by Ben Tasker's group a few years ago called posterior regularization. So we have EM and hard EM, and we have constrained hard EM and constrained EM. And the question is which version to use, right? So there's a lot of literature on EM versus hard EM. And maybe the common view is that if you have good way to initialize the model, hard EM is doing better than EM. But, different problems behave somewhat differently. And as I said, it exists for hard EM and EM, and it exists also for CODEL versus PR. So what I want to give a few slides on is a new work that we've done that actually unifies this perspective. Basically, something that we call unified expectation maximization that gives us a family of EM algorithms parameterized by a single parameter, lambda, that provides a continuum of algorithm from EM to RDM and also from constraint EM to constraint RDM by tuning one single parameter. So basically, the idea is to start with Neal and Hinton's definition or formulation of EM, this entropy formulation, and essentially add one parameter, this lambda here, that changes the entropy of the posterior. If you think a little bit about it, different values of lambda are going to give you different EM algorithms. In fact, you can think about them as giving you different values of the posterior from, this peaky one, which corresponds to hard EM, to the original one that corresponds to EM, and many things that could be in the middle. I don't want to dwell on this, but in the paper we actually give conditions for which values of gamma produce which type of known algorithm. But the thing is that you can change lambda, gamma, and in the no constraint case, you're going to change algorithms from hard EM to EM. In the constraint, and you will also get, as a special case, deterministic annealing algorithm that was suggested by Jason and Noah Smith a few years ago, and a few other algorithms that were known in the literature. And in the constraint case, you're going to get both CODEL, PR, and some other versions of CODEL. And most interestingly, you're going to get infinitely many new EM algorithms that we couldn't express before. So just to illustrate the type of things you can get here, I'm showing here one set of experimental results that have to do with parlor-speech tagging. What you see here is a collection of curves that depend on the level of initialization, how many examples we initialize with. On this side, you have EM. On the other side, you have hard EM. And what you can see is relative performance that is relative to EM. And you can see that if I start with no initialization, basically, EM is doing best. I cannot improve over EM. But as I initialize a little bit better and better, 5 examples, 10 examples, 20 examples, 40 to 80 examples, and so on, I improve. And the interesting thing here is that in almost all cases, the best result that I get is somewhere in the middle, between EM and hard EM, with some parameter lambda, gamma, that we tune on a development set. So, and we see the same kind of behavior on several other problems that we tried on. So here is something for you to try. Replace your EM with UEM and see what happens. Okay, so just to summarize this part, my goal here is really to talk about how to use constraints as supervision using this constraint-driven learning algorithm. Basically, the idea is to introduce domain knowledge as a way to help guiding semi-supervised learning. Constraints could be things like the sentence must have at least one verb, or a field Y can appear only once in the citation, and so on. So I talked about CODEL and referred also to posterior regularization and UEM. And there's a lot of literature related to this that you can take a look at. You know, most of it is cited and explained in the UEM paper that was presented in NACL last summer. The final thing I want to say is I want to talk a little bit about inference. And I want to talk about inference in a different way that we typically talk about inference. Typically, we talk about algorithms. Can we take this inference algorithm and massage it a little bit to improve it? And I want to give a slightly different perspective of the inference problem here. Basically, I want to ask the question, can the kth inference problem be cheaper than the first? So again, I'm talking now about this box. And as I said, rather than thinking about how to solve it, I'm going to present the following questions. I want to think about inference from an amortized perspective. So the interesting thing about the way we use in NLP, ILP solvers, or in general do inference, is that we don't do it once a week for a big problem and then forget about it. We actually solve it many, many times, once per sentence or multiple times per sentence. So beyond improving the inference algorithm, which is, of course, an orthogonal important goal, what else can we do? So I want to start with the observation. Here is a parlor-speech tagging problem. Here is another sentence that I want to parlor-speech tag. And in both cases, the solution is the same solution. So these are different sentences, completely different sentences. Nevertheless, the output structure is the same. And the question is then, after inferring the parlor-speech structure for S1, can we speed up the inference for S2? So this is what I call the amortized inference question. I want to formulate the problem of amortize as reducing the inference time over the lifetime of the NLP tool. And the solution actually is that it's possible, even though what we have here is preliminary, but I think very promising results, where we can give a family of exact inference schemes for this and a family of approximate solution schemes that show that actually you can cut significantly the number of times you need to call a solver if you know how to do it. And one important issue is that the methods that I'm going to present are invariant to the underlying solver. I don't care whether you use a commercial solver, dual decomposition, search technique, what have you. This is a black box for me. I'm reducing the number of calls to the solver, regardless of which method you're going to use. And you'll see that the improvements are quite significant in terms of number of calls to the solver. Why is there hope even in looking at problems this way? So this is a graph that shows the number of examples of a given site when I'm looking at parlor-speech tagging on GigaWorld as a function of the number of tokens. And this is the number of structures, unique part-of-speech tag sequence that I get. So you can see that the number of structures is much smaller than the number of sentences. You all know that. Similarly, I'm looking at dependency parsing. Again, the red curve is the number of examples. The black curve is the number of unique structures. Again, much smaller number of structures than number of inputs. And the same thing happens for SRL, where in this case the x-axis is the number of arguments per predicate, because this is the complexity parameter that I care about. And moreover, it's not only that the number of structures is smaller, you can even look at the distribution of the structure. It's very skewed. It's kind of Zipfian distribution. I mean, it looks like this. I have to do this, compute this distribution for each number of tokens separately. But really what you can see is that there's a small number of structures that occur very frequently, and most of the structures occur very infrequently. And you know, a lot of you that have looked at this data probably have made these observations also. So the question is, okay, so can I use this? Right? So the statistics shows that many different instances are actually mapped into identical inference outcomes. Right? Can I exploit this information as a way to save inference costs? And I'm going to do this in the context of 0-1 linear programming, because most of the formulation that we're using in NLP are actually 0-1 rather than integers. So basically, this is the linear program that I have. And I'm going to basically give you a couple of examples that will illustrate what I'm trying to do. So think about these two problems. I have two ILP here. I'm going to say that two ILPs are in the same equivalence class if they have the same number of inference variables and they have the same feasible set, which basically means they have the same constraints, modular renaming of the constraints. This is an important thing because renaming is crucial here. So these two problems are in the same equivalence class, right? They have the same constraint set. Note, I'm going to XP in this case, this 0-1-1-0 is the optimal solution. And by CP or CQ, I'm going to denote the objective coefficients of the problem. Notice that in this specific equivalence class, what I have here is that for those variables that are active in my optimal solution, the coefficients did not decrease. They went up or stayed the same. And for those inactive variables, those that are zeros in the optimal solution, actually the coefficient of the objective function did not increase. It's rather easy, if you think about it a little bit, to actually prove the following theorem, that under these conditions, the optimal solution of Q is the same as the optimal solution of P. I'm not going to prove it, but if you think about it, you can prove it to yourself. Basically, what you get is the following theorem. I'm just adding some confusing notations because I want to compile these two conditions of dominance. Dominance has to be looked separately for the active and the non-active variables, so I'm using this delta notation here. But basically, the theorem says that under these conditions, where the dominance happens, without solving Q, I can guarantee that the optimal solution of Q is the same as the optimal solution of P. Second observation. Let's think about these two ILP problems, P1 and P2. And a third problem, Q. It so happens that P1 and PQ have the same solution. And it so happens that the objective function of Q that belongs to the same equivalence class is really a conic combination of the objective functions of P1 and P2. Conic combination, basically linear combination with positive weights. And it turns out, again, it's not hard to show that in this case, the optimal solution of Q is the same as the optimal solution of the P's. So basically what I have, okay, this is the theorem. The important condition here is that when I have a collection of problems, the new problem is a conic combination of the old objective function. And in this case, I maintain the solution. I know ahead of time the solution. So geometrically, you can think about it this way. So I have multiple solutions, P1 and P2, multiple objectives, CP1 and CP2. And I'm looking at, and they have the same maximizer here. And as a function of that, all the cone of CP1 and CP2 share the same maximizer. And I can combine this result with the dominance result that I showed before, and basically I have the following theorem that summarizes all we know, is that on one hand I need to have a conic combination, and on the other hand I have to have this dominance relation, so I can change separately the coefficients of the active variables and the coefficients of the non-active variables, and under these conditions, without solving Q, I can guarantee that the optimal solution is the same as the optimal solution of the PIs. So these are really nice, I think, nice conditions, basically extension of a theory that was known for many years, sensitivity analysis for linear programs. Here we do it for integer linear programs. And the key question is, okay, so you have some theorems. Will the condition of the exact theorems hold in practice? And I want to argue that intuitively, these statistics that I showed before guarantee or almost guarantee that they will, right? So there are very few structures relative to the number of instances, so there is some collapse here, and these theorems in some sense capture this. Of course, the question is, are the conditions that we phrase too strict or not? And we can actually relax them, right? So to guarantee that the condition actually be satisfied, we could relax them and move to approximation methods. And these have the potential to actually give us broader conditions under which we will gain something from this collapse from number of examples to number of instances. It turns out that indeed we get better speed up, but we hardly lose in accuracy. So what kind of approximation I can make? So I can start with two very stupid approximation methods. Basically take, within any equivalence class, take the most frequent solution and always choose this one. Or take one of the k frequent solutions, choose which one has the highest score, and choose this one. I didn't need to have theorems in order to do this. What I really want are the approximation theorems for the theorems that I showed, and let me just focus on the last one. So I need to satisfy the conic combination condition, and rather than the dominance condition that I had, I'm going to relax it by epsilon. I'm going to say the coefficients of the objective are going to dominate the old objective, but I'm going to allow some slack of epsilon. What do we get? So we do this experiment on semantic labelings. You know the problem. I just want to mention that we're basically using Gorabi 406 as our solver, and for amortization, we've collected, before we started, 250K SRL inference problem as our cache. Of course, the larger the cache, the better you'll be. Here is what we get. So I want to look at speed up, and I want to look at performance. So in terms of speed up, we get from baseline and the three theorems, I basically get a speed up of around 2.5, which is quite nice, I think. So basically, all I need to call, I need to call the solver only on 40% of the instances that I have. And with the approximation method, I get even better speed up to about 3 or a little bit over 3. What happens to the results? Of course, the exact do nothing to the results. It turns out that outside this, what I call the stupid approximation methods, the approximation methods that are built on our theorems actually do not lose a lot in accuracy. So we actually maintain the accuracy and get speed up of about 3 times. So, of course, you can ask many questions here. I want to summarize this because my time is basically up. So basically what we showed is that inference can be amortized over the lifetime of an NLP tool and give significant speed up. And this is really preliminary result. This was presented in EMNLP earlier this summer. There are many, many questions that we can ask. First of all, we dealt with the whole problem. I think there are many decomposition methods that we can use in order to gain even more. Possibly when we put together the components using some methods like Lagrangian relaxations or other. We haven't even used the approximation with warm start. That is going to help even more. We haven't quantified this yet. And there are interesting relations, I think, to lifted inference. Basically, some abstraction methods that are used in probabilistic inference in order to gain even more over this. Okay, so let me summarize the talk. Basically, I wanted to present constraint conditional models. So it's an ILP-based formulation framework that allows one to augment statistically learned models with declarative constraints, with the goal of facilitating the incorporation of knowledge in order to support global decisions in expressive output spaces in NLP problems. One of the nice things about this is that it allows us to maintain modularity, software engineering principle if you want, and tractability of training. And there's a lot of work on showing that you can do powerful yet modular learning and inference for high-level tasks in this. Where the philosophy is that you learn multiple interdependent components and via inference put this together to make coherent decisions. So I talked a little bit about learning issues. There's a lot more done and things that can be done on learning here. I talked about amortized inference. Again, there's a lot more that can be said about inference. I think that this is a very interesting direction, and I'm interested actually in people's perspective on this. I want to finish with a plug. Check out our tools. They are all available from our webpage, my group's webpage, a lot of demos, and the tutorial that gives a lot more details on this. And thank you. Questions?
So I've done a few questions I want to try to ask them. One question is on constraint conditional models. So you're training locally conditioned classifiers first and then combining them. Does it make sense to do this hierarchically, for example, in a pipeline setting? There's a problem that what you would want to do, for example, is say you have your local part of speech tag preferences based on the words, and then you combine those using a global model to get posterior probabilities globally of the individual part of speech tags or configurations thereof, and then you use that to feed into SRL or something. The problem is that if you're using ILP at any stage, you're not getting posterior probabilities anymore. You're just getting one value.
Okay, so first of all, I think it does make sense to do hierarchically when you have big problems. And the question of getting only best versus getting top 5 is actually a very interesting question. I mean, it's not easy. There's been a little bit of work. There should be more work on how to get the top 5 in an ILP solver, or the top K in an ILP solver. It's not an easy problem. But I agree that if you would get that, then it would facilitate incorporating things in a hierarchy like the one you suggest.
Well, even getting top 5 is not quite analogous to what you're doing at the base level.
Yeah.
Where you're getting actual probability.
Right. But I agree. I mean, so
there's several ways around this. I'm just wondering about the including sampling and calling the solver many times and so forth.
Right. So I don't have a set solution for this. But in many instances, we know that getting the best is the best thing we can do. So maybe that's the case here too. Although I'd like to see are able to actually produce some probability distribution, even if not over all solution, over top solutions. Yeah, I think this is a good goal to have. I don't think that we know how to do it well today. Yeah.
Has there been much work on learning constraints?
Okay, that's a good question. That is actually the top one question that I get on this. So there has been some work, and there could be a lot more work. I want to say one thing. Philosophically, I'm not so concerned about the fact that we are sometimes just declaring constraints. I think in many cases we have a lot of knowledge about problems that it would take a lot of data, and maybe data from other modalities, maybe things that we can't even learn easier, and we have them, and I don't see any problem with incorporating them declaratively into the model. That said, in several problems, you want to learn constraints. And I've seen a few problems. I can give you some pointers. We've done it only in one problem that I can think of now, when we are extending SRL to include also some other predicates, and we learn constraints. But I think there are other works by other people that have done that. Yeah, you know, it's not easy. First of all, you need to have data. Second of all, you have to define some language into which you want to learn the constraints. And there are some issues.
You mentioned in the simple example of bibliographic citations seem like they would be very easy to learn.
Yeah.
I just don't know whether that's an artifact of such a simple example or whether...
I think the constraints are simple. Again, the language is quite expressive. So you will need a lot of data to learn this. And you also have to be ready to the fact, this was a surprise to me, I must say, that in most domains, the constraints do not hold. I mean, they hold in expectation, but the data is, every data violates all constraints that you can come up with. So you should be able to allow for that. Yeah.
Just a related question. I was wondering if you sort of have a philosophical view on whether information should go into the features of the base models or into the constraints. So for example, let's say I gave you a list of 10,000 journals, and I wanted you to use that to improve your information extraction citation. Do you include that as a feature in the base model?
Okay.
Or do you make that a constraint?
Okay, so two issues. That's the second most popular question. So there are two issues here. So first of all, what's the difference between features and constraints? So mathematically, you can say they are the same. I actually have slides on that, but never mind. So mathematically, they are the same, right? So it's a mapping from x cos y to a real number or 0, 1. Philosophically, they're very different. And let me illustrate one difference before I get to the general case. So first of all, if your models are only f of x, like in SRL, where all you learn is classifiers over x, your constraints are the only way for you to relate the y's. Otherwise, you don't have it. So that's one difference. In general, when your features are also phi of x, y, there is still a very significant difference between constraints and features. Features in NLP are propositionals. You know, before my target word, I see this part of speech, and after it, I see this word. They're lexical, propositional. In constraints, typically, you have quantified things. You know, if you have, whenever you have a phrase of this type, you must have a phrase of that type. So they're kind of different animals. And you could propositionalize it and make them features. You'll get a lot more things, and then you'll have to learn parameters for things that you know ahead of time. So that's really the trade-off here. If you know that you cannot have phrase of type N, a state of type A and type B in the output, you can still propositionalize it and write it in features. You'll get a lot of features, which means you'll have to learn a lot of parameters. So, and as I said in the talk, I have two slides that discuss this. But it's a good question, right? Because you always want to think about it. I mean, how do I want to model the problem? But I think in some cases the solution is easy. In some cases you have to think more.
Okay, let's thank Dan again.
Okay, thanks.